Hello everyone. Today we are continuing with grade 12 physical sciences, paper 2 from the November 2022 section. We're on question 6. Questions 1 through 5 have been done in previous videos, so you can check those out first if you haven't already. Here we're focusing on question 6, and let's get straight into it. So at first glance, question 6, it's out of 21 marks. There's about 6 sections to it, and section 6 has about 4 subsections. Okay. We can see there's some big questions already. Like question 6.5 is for 5 marks. Question 6.2 is for 4 marks. It looks like a thermodynamics question. Or reaction kinetics rather, perhaps. So quite a bit of math going to be going on in this question. So this is just some, thoughts at first glance. Looking at the question, I see they're talking about Le Chatelier's principle. They've given us a graph at the bottom of reaction rate versus time. Okay. All right. Okay. So let's get into the question. So carbon reacts with sulfur according to the following balanced equation. Okay, so carbon plus 2 sulfur gives carbon disulfide, and they tell us that the enthalpy of the reaction is positive here. Okay, just highlight that. So what does that mean? So a positive enthalpy, so delta H greater than 0 means it's positive, which means we have an endothermic process. And endothermic basically means that it absorbs heat. So for this reaction to happen, heat is absorbed from the surroundings. Or you might have to heat it up yourself in order for the reaction to happen. Okay. Cool. So interesting, we have an endothermic reaction. The system reaches equilibrium at temperature T in a sealed 2 decimeter cubed container. Okay. The Kc value is 9.4 at temperature T. Okay. So Kc 9.4 at T, temperature T, sealed to, okay, equilibrium. Okay, so sometimes it helps as you read through the question just to write down the information as you get it, because sometimes if there's a lot of words, it's harder to see. So the first thing is that delta H is positive. Okay, so they give us temperature T, we're given volume equals 2 dm3, and at T, Kc equals 9.4. Okay, so just some information given. It's much easier for me to look at this than to look at all this, but it's your preference. Okay, so state Le Chatelier's principle. So of course there's always different ways you can phrase it, but the key statements or phrases required would be something like this. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. So this is a very textbook definition. It can be difficult to memorize these as they are, so sometimes it might make more sense you can rewrite it in your own words, but the important parts are it's a closed system, the system is disturbed, and then a new equilibrium is introduced that cancels the previous disturbance or opposes it. So if we have some closed system and we increase the volume, we've now changed the equilibrium because the volume has changed, or the concentration of one of the reactants has changed. Therefore, we will reach some new equilibrium where the change in volume doesn't matter, basically. So yeah, you just have to either memorize the definition as you have it or try and think of it in your own words and just make sure you have the key phrases in whatever answer you put down. Okay. Carrying on. At equilibrium, 1 mole of carbon disulfide is present in the container. Okay. Some more information. So at T, Kc equals 1.9, and there is, so the moles of carbon disulfide equals 1 mole. Okay. Calculate the concentration of S at present equilibrium. Okay. So, a couple of things to remember for this question. Okay, this is question 6.2. The first thing is, in equilibrium calculations, we do not include anything that is solid. We only deal with gases and liquids, okay, things that can have a concentration. Solids can't really have a concentration, so we don't include them in our equation. So the equation is Kc equals products over reactants. So our product is carbon disulfide, so the concentration of carbon disulfide over the concentration of sulfur. Now remember, the stoichiometric coefficient of sulfur here is 2. So that means in our constant equation here, we have to raise this to the power 2. Okay. Now let's substitute in the values we have. So we know that Kc is 9.4. We know that the concentration of carbon disulfide is 1 over the volume, which is, what is the volume given? So the volume given was 2 decimeter cubed, right? Okay. So 1 mole over 2 decimeter cubed divided by whatever S is to the power 2. So I hope you see that this simplifies to 0.5. I mean, it's just 1 over 2. And then we want to make S the subject of the formula. So we'll take S squared. Bring that this side, so 0.5 over 9.4. And then we want to get rid of this. So we'll just take the square root both sides. And therefore S equals, doing this in your calculator, you should get something like 0.23. And remember, we had decimeter cubed here and mole here. So our concentration is moles per dm3. Okay. You can also write it like this. I mean, both ways work. Okay. All right, good. So let's clear this up. Come back here. Okay, that's question 4. Question 6.2, sorry. Carrying on. The volume of the container is now doubled at temperature T. After a while, a new equilibrium is established. How will the amount of sulfur change as the new equilibrium is established? Choose from those examples. Okay. So what we got to look at is we got to look at our equation that they've given us here. Okay. So let's have a look at this equation. So we've increased the volume, okay? And what we got to notice is that we actually have more sulfur than carbon disulfide, right? Because this is 2 and this is 1. There's an imaginary 1 there. So there's more gas on the left-hand side of the equation. And usually what happens is when you increase the volume, the system wants to occupy that new space, okay? And in order to do that, it will move in such a way to produce more gas. So there's more gas on the left-hand side of the equation because it's 2 sulfur compared to 1 carbon disulfide, like stoichiometrically, the molar ratios. So the equation is going to move in the reverse direction. It's going to produce more sulfur. There'll be less carbon disulfide. So if volume increases, if volume increases, then the amount of sulfur would increase. Okay, so sulfur would increase. Okay, all right. Explain the answer to question 6.3 in terms of Le Chatelier's principle. Okay, well, that's just what we've done, right? But you can have a more formal explanation, and these are some of the key points you'd have to include in that explanation. Increasing the volume will decrease the pressure. The reaction that produces a greater number of moles of gas is favored, so the reverse reaction is favored, and of course in the reverse reaction we have sulfur, so more sulfur is formed. Okay, question 6.5. If the concentration of carbon disulfide changes by X, write down the expression for the equilibrium constant Kc in terms of X. Okay, so we're not actually gonna calculate anything. We're just going to work in terms of X. All right. Okay, this is a bit of a big question, but all right. I suggest for these questions making a table. Okay. So let's do that. So question, still on my highlighter. Maybe let's do this in blue. Question 6.5, okay. So they told us that okay. So show all your working, no simplification of X is required. Okay, I didn't see that. That actually makes it a bit easier. All right. If the concentration of carbon disulfide changes by X, write down an expression for the equilibrium constant of Kc in terms of X. Okay. So again, from our equation, we're not dealing with carbon. Carbon's a solid. We're only dealing with gases in this question. So let's make a table. So let's start with our initial. Okay. Let's make a column for sulfur and another column for carbon disulfide. So our initial here, we've already calculated. This is 0.23. And this was 0.5, right? Half over 10. No, not half over. Oh, I cancelled it out. Half over 1 over 2, which is half, yeah. So 0.5. Okay. So what they've told us, the condition they've given us, is that the volume is doubled. Okay, volume is doubled. So when the volume is doubled, what we know is that our concentration should be reduced by half, yeah? Because concentration is moles over volume. So if this thing increases by 2, then we'll have something like this, N over 2V. You can factor out half. So your concentration is now half N over V. And if C equals N over 2V, then we can see that our concentration is essentially reduced by half. Maybe my mathematical representation of this is a bit messy, but it gets the point across that if V is doubled, C is halved. Okay. Okay, so we need to halve our concentrations. Okay. So our new concentrations would be, this halved would be 0.115, and this will be 0.25. Okay, good. So that's our initial. Now, what about our change? Okay, so our change is X, yeah? Okay, so the change for carbon disulfide is X, and then from our equation, whatever this is 1 is to 2. So whatever happens to this happens twofold to sulfur. So this would be 2X, okay? And then at equilibrium now, okay, what do we have? Okay, so because these two are on opposite sides of the equation, whatever happens to carbon disulfide, it would be the reverse that happens to sulfur. So if carbon disulfide is changed by X, then we need to add X to sulfur. So this would be, okay. All right. So now we have our, this is a very messy table. But I hope it gets the point across. Now we have enough information to write Kc. So it's product over reactants. And then remember that we have to raise this to the power 2. Okay? And they said we don't have to simplify, so this is good enough. Okay, good enough. Okay, let's move on to 6.6. The reaction rate time graph below represents further changes made to the equilibrium mixture. The volume of the container is kept constant. Okay. What does the parallel lines between TA and TB represent? Parallel lines. Okay. So I suppose they are referring to these lines here. And these lines simply represent the rate of the forward and reverse reactions being equal, because they're the same. So the reaction rate is the same, yeah? The lines are exactly the same. The equilibrium constant is the same. The reaction rates are the same. It just means that between TA and TB, the forward and reverse reactions are basically equal, right? That's what those lines mean. Okay, the next one, what change was made to the equilibrium mixture at TB? Okay, so at TB, we have a sharp jump in, we have a very sharp jump in over here, which is our forward reaction. So that would most likely happen if we increased our reactants. So perhaps S was increased, so an increase in S could result in that. Give a reason for the sudden change in the reaction rate at TC. So okay, here we have a decrease in the forward reaction. So I mean, you could say something like the concentration of the reactants was reduced, but it's more likely that something like maybe just the rate of the reaction decreased. Because what we should see is if there was a dip here, we should have seen a spike in the reverse reaction if the reactants were reduced. So more likely, maybe something like temperature was decreased, so the reaction just slowed down. Okay. Oh, then it just asks us to explain. Okay, so you could say the rate of the forward and reverse reactions both decrease, right? Like I said, if it was a change in concentration, this one should have increased. But because they both dip, right, then the reverse reaction is favored faster than the forward reaction. So this is probably a decrease in temperature, which favors the exothermic reaction. So they kind of want quite a bit of detail from you for this. I mean, it's 3 marks. So they want you to say, okay, Both reactions decrease in rate, but the reverse reaction not as much as the forward. And because it's an endothermic process, this is where this comes in. It's endothermic. That means endothermic process, its reverse would be exothermic. So if you reduce the temperature, the system will want to try and make a change that doesn't change the temperature. So it's going to release heat. And therefore, the only way to release heat is to work in the exothermic direction, which is the reverse, because the forward is endothermic. So that's where the extra marks come from. That's a tricky question to see that. That's why it's 3 marks. So they want you to say that, and then you'll get the full marks. Yeah, that was quite a tricky question, guys, but I hope this helps. I hope we understand a bit more about thermodynamics and how to answer these questions after this video. Thank you.